So this is a question on half-life and radioactive decay. I'll give you an opportunity to pause the video now so you can have a go at this question yourself, and then we'll go through it together in a moment. Right, so let's start off by reading and highlighting the information that we've got and then working through the questions together. So the graph shows how a sample of barium-143, a radioactive isotope with a short half-life, decays with time. So then we can look at the graph. So it's got the classic half-life exponential curve, or exponential decay, sorry. On the y-axis, we've got the number of barium-143 atoms going up in thousands. And then along the bottom, we've got time in seconds, so going up in kind of blocks of 10 seconds. Okay, so the first question, what is meant by the term isotope? So this is a definition question. So we just need to give a simple definition of the word isotope, and it's worth 1 mark, so it's just a short phrase or sentence. So we should know that an isotope is an element with the same number of protons and a different number of neutrons. So this is the kind of question where actually you could get the mark for giving a slightly different kind of definition. So instead of saying number of protons, you could say atomic number. So you're showing that you know that the atomic number is the number of protons. And instead of number of neutrons, then you could say that it has a different mass or atomic mass. And that would be equally as acceptable. So the next question, what is meant by the term half-life? And again, this is 1 mark, so it's asking us to give a definition, and we would give this as the amount of time for the activity to decrease by half. Okay, so that's 1 definition that you could give. But similarly, you could, instead of activity, you could say number of barium-143 nuclei, so the number of nuclei of this isotope to decrease by half as well, and you'd still gain the marks for that. Okay, so the next bit, use the graph to find the half-life of barium-143. So we've got this graph here, and we want to find the half-life of barium-143. So you need to practice doing this. It's always going to be the same sort of curve when we're talking about half-life. So if this is the activity at the beginning, so the count rate, the number of barium-143 atoms, then we just need to halve that. So half of 4,000 is 2,000. So we're going to go to 2,000, get a ruler, and we want to draw across to the line, and then draw down from the line to the x-axis. And you should be able to see if that's 10, 11, 12. So we would say that that would be 12 seconds. And it's okay, it's acceptable to draw 1 line for this, but you can always double check because the half-life should always be the same. So therefore, the amount of time it takes for this activity to decrease by half should be the same as it did from 4,000 to 2,000. Well, half of 2,000 is 1,000. So if we went across from 1,000 to the curved line and then drew down from that. So this is 20, 21, 22, 23, 24. So the first half-life is 12 seconds, and then the second half-life is 12 to 24, which is also 12 seconds. So we can quite confidently at that point say that the half-life is 12 seconds, because it's not just the first one, it's the same for the second half-life as well. So on to the next part. Humans take in the radioactive isotope carbon-14 from their food. After their death, the proportion of carbon-14 in their bones can be used to tell how long it is since they died. Carbon-14 has a half-life of 5,700 years. Okay. So life on Earth is carbon-based. So the food that we eat has got carbon atoms in it as part of the molecules that make up the food. Some of those atoms are going to be, or some of those some of those atoms are going to be carbon-14 rather than other isotopes of carbon. You eat during the whole of your life. And then when you die, you obviously stop eating, so you stop taking in new carbon-14. So we can use that to trace back when it was that you had your last meal. And we are talking about thousands of years here. We're not talking about someone who died a couple of weeks ago. So a bone in a living human, contains 80 units of carbon-14. An identical bone taken from a skeleton in an ancient burial ground contains 5 units of carbon-14. Calculate the age of the skeleton and show clearly how you worked out your answer. Okay, so let's write out the information that we've been given to start off with. So, one half-life is 5,700 years. So we're being asked to find out how old this skeleton is. So logically, we need to think about how many half-lives happened in order to get from 80 units to 5 units. And then when we know how many half-lives have happened, we can then work out how many years that must have been. So we're going from 80 units to 5 units. And we want to know how many years. So that's a question mark. How many years? Okay. What some people do to start off with is they'll just do 80 divided by 5. But we need to remember that what we're doing each time is halving. So if we have a calculator and we've got 80, so we divide that by 2, and that's the first half-life, and we've got 40. So we're going to divide that by 2 again for the second half-life, and that's 20. We do it again for the third half-life, and we do it again for the fourth half-life, and we've got to 5. So therefore, if that's 4 half-lives, okay, we've got 4 half-lives. 1 half-life is 5,700. So 4 times 5,700. And that gives us 22,800. So 22,800 years, therefore, is the age of our skeleton. So next part. Why is carbon-14 unsuitable for dating a skeleton believed to be about 150 years old? So this is what we need to kind of think about. Let's pretend for a second that that this graph is a carbon-14 graph. So the scale on here would be talking about thousands of years. This here would be 5,700 years, because that would be the first half-life. So that'd be, say, I don't know, 6,000 years, 12, whatever. It's going to increase. So if we've only got 150 years, that's going to be a tiny change in time, really, compared to the even 1 half-life. So therefore the change in activity would be very small. So we could summarize this by saying there would be very little change or decay as the time is short compared to the half-life. And that would definitely get us that 1 mark. So then the last part. So this is a 3-mark question. It's given us quite a lot of space. So we need to make sure that we read it really carefully so that we can attain all 3 of those marks. So the increased industrial use of radioactive materials is leading to increased amounts of radioactive waste. So let's highlight that. That's an important thing to be thinking about. So some people suggest that radioactive liquid waste could be mixed with water and then safely dumped at sea. So that's kind of a bit of data, really. That's the statement that some people have made, apparently. Okay, so it can be mixed with water and safely dumped at sea. Do you agree with the suggestion? And then explain the reason for your answer. So with questions like this, you might get a mark for agreeing or disagreeing. That depends on the demand of the question. So if this is at the very beginning of like the higher paper, for example, you might get a mark for saying whether you agree or disagree, because there'll be crossover with the foundation. However, it's probably unlikely, and you'll get marks for either agreeing or disagreeing, but it's the explanation, the science behind it, that's actually going to get you those marks. And in situations like this, it's actually unlikely that they'll you gain marks for going one way or the other, because there's kind of scientific merit for both ideas. So let's split this down the middle, and we are going to look at arguments that agree with the statement, and we will also look at arguments that disagree. Okay, so if we're agreeing with the statement, we want to say why it might be acceptable that it's safely dumped at sea if radioactive liquid waste is mixed with water. So this mixed with water is, I guess, the key idea, because that means it will be diluted, okay? And it could be diluted enough if lots of water is used. So then maybe we want to elaborate a little bit on that and talk about what we mean by dilution. So we are reducing the concentration of the waste. So therefore the particles are so spread out that that then they're not as harmful, or it's less likely to cause harm to an individual organism. But we'll come on to that in a minute. And it's the factors then again that it's talking about safely dumping at sea. So it's not talking about putting it out near human habitation. So it might be okay or less harmful if dumped in the middle of the ocean. I personally think that's stretching it a little bit, because you've still got a lot of organisms that live in the oceans, and there's currents and what have you that will move it around. So I guess you'd have to really argue that it's away from land organisms, at least, I guess. I think they're a little bit of a stretch in terms of that argument, but you'd still get marks for writing that sort of thing. So on to the disagreement. Again, the marks that you get will, or the kind of thing you're expected to write might depend on the demand of the question. So again, if this is at the very beginning, you're probably more likely to get marks for saying things that are very vague, like pollution of oceans or sea. Pollution is a very general kind of phrase. People, when they're talking about sort of energy resources and talk about fossil fuels, you know, you don't always get marks for saying they cause pollution, because it is just a bit vague. Being able to talk about things like carbon dioxide or whatever is what's more likely to get you marks. So in this case, we want to talk about what kind of problems this is going to cause. And it's all to do with the fact that it is ionizing radiation. So if it's ionizing radiation, it can cause mutations or harm, I suppose, if we want to be really vague, to living organisms. I guess you could say then that it can lead to the organisms dying, but also the impact is on the food chain. So if the organisms die, then there's going to be fewer of that organism to feed the next thing up in the food chain. Equally, if that's taken in and become contaminated with the radioactive waste, then that could impact the thing that eats it, like its predator, and then that can cause mutations if there's still some of that radioactive material in the organism. And then most importantly, and this is why radioactive waste is such a problem, whether it's dumped in the sea or not, and that's because it takes a long time to decay to a safe level. And because it takes such a long time to decay to a safe level, if you've then contaminated the oceans, or if you're adding this diluted waste before it's decayed to like background radiation levels, basically, then you are going to be increasing the concentration. So, you know, this might be okay once, but the more that you are adding to it, the more likely that it's going to cause long-term problems because of the ionizing properties.